Hello everybody. In this video we are going to continue with chapter 11, probability, and specifically 11.2, probability assignments. So the first thing we're going to look at is probability rules. So these are the basic rules of probability. Rule 1. Any probability is a number between 0 and 1. That is, the probability of an event A satisfies this inequality. It has to be between 0 and 1, including 0 and 1. If the probability of an event is 0, then the event never occurs. Likewise, if the probability is 1, it always occurs. Now we have rule number 2. All possible outcomes together must have probability 1. That is, the probability of the sample space U is 1. So the probability of the sample space has to be equal to 1. Rule number 3. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. Two events that have no outcomes in common and hence can never occur together are called disjoint events or mutually exclusive events. So the probability of A or B is equal to the sum of the individual probabilities. This is known as the addition rule for mutually exclusive events. Rule number 4. The event that contains the outcomes not in A is called the complement of A and is denoted by A prime. So the probability of A prime is 1 minus the probability of A, or the probability of A is equal to 1 minus the probability of the complement of A. So now we'll do example 11.5. And it says, when people create codes for their smartphones, the first digit follow distributions very similar to this one. So these are the first digits, and this is the probability that people will choose it as the first digit. Part A, find the probabilities of these events. A, the first digit is 1. So the probability of event A is simply going to be the probability of the first digit being 1, which is given to us on the table, and it's 0.3. Probability of B, the first digit is more than 5, so that's just going to be the sum of the probability that the digit is more than 5. So probability that it's 6, plus probability that it's 7, plus probability that it's 8, and summing the probability that it's 9. And this is simply going to be a total of 0.221. The probability of C, which I'm going to do over here, the probability of C, first digit is an odd number, so that's just going to be the probability of 1 plus the probability of 3 plus the probability of 5 plus the probability of 7 plus the probability of 9. So then again, all we have to do is a sum, and it's going to give us 0.603. So 60.3%. For part B, find the probability that the first digit is number 1 or greater than 5. So it's the probability that it's 1 plus the probability that it's more than 5 was the same as probability for B in the past part of the question. So all we have to do then is add 0.300 plus the probability that we found for B, which was 0.221. And this is a simple addition that is going to give us 0.521. And then for part 2, they ask us what is the probability that it's not 1. So remember that the probability that it is not 1 is the same as 1 minus the probability that it is 1. So this is just going to be 1 minus 0.300. So this is going to be 0.700. And then finally we have part 3 that says find the probability that it's an odd number or a number larger than 5. So that's the probability of A or B. So that means that it's going to be the probability that it's 1 plus the probability that it's 3 plus the probability that it's 5 plus the probability that it's 6 plus the probability that it's 7 plus the probability that it's 8 plus the probability that it's 9. So we have to add all these up. And all this is going to equal 0.721. So now we're going to talk about equally likely outcomes. In some cases, we are able to assume that individual outcomes are equally likely because of some balance in the experiment. For example, flipping a balanced coin renders heads or tails with an equally likely probability of 50%, and rolling a standard balanced dice gives the numbers from 1 to 6 as equally likely, with each having a probability of 1 over 6. Suppose that in the previous example, 11.5, we consider all the digits to be equally likely to be selected. Then our table would be as follows. So notice that each digit would have the same probability of being selected, which would be 10% for each since there are 10 digits. So now let's take a look at geometric probability. Some cases give rise to interpreting events as areas in the plane. Take, for example, shooting at a circular target at random. What is the probability of hitting the central part? So the central part is this green circle, and it tells us that the radius is 1/4 of the full radius, right? It says radius over 4 right here. Therefore, the probability of hitting the central part is going to be the green area divided by the total area, as you can see here. And that's going to give us 1/16. Now let's focus on example 11.6. And it says, Lydia and Rania agreed to meet between 12 and 1 p.m. The first person to arrive will wait for at most 15 minutes. If the second person does not show up in this time, the first person will leave and they will arrange to meet at some other time. Assuming that their arrival times are random, what is the probability that they meet? Okay, so notice that they have 1 hour to meet between 1200 and 1300 hours. So let's suppose that Lydia arrives X minutes after noon, and Rania arrives Y minutes after noon. There's one thing to take into account here, and it is that X must be less than or equal to 60 minutes, and that Y has also the same condition. But there's another thing. The difference between their arrivals has to be 15 minutes at most. So that means that the difference between arrival time Y and X must be less than 15 or equal to 15. Why do we use absolute value? Because these two can be in either order, right? One of them can arrive before the other one. So now we're going to use geometric probability to solve this problem. So for this, we're going to use a Cartesian plane. Now notice a few things here. First of all, let's consider that X is Lydia's arrival minute, right, afternoon, and that Y is Rania's. So notice that the set of all possible intersections between them is the whole area of this square that we see here. So that means that the probability or the total outcomes are going to be 60 squared, the whole area, right? Now, because of this condition, which is an inequality, notice that we can solve this by saying that y minus x must be greater than or equal to negative 15, but less than or equal to 15. And then solving this, we're going to get x minus 15 is less than or equal to y, which is less than or equal to x plus 15. So notice that x plus 15 is this graph here, right? This is a line. So this is y is equal to x plus 15. And then this one is obviously here, y equals x minus 15. And y must be between those two lines. So the arrival time for y has to be within this blue area. So the solution will be the area of this blue part divided by the total area of the square. So this is going to be 60 squared minus, and notice that here we have two triangles that are equal to each other and that are isosceles. Notice that this is an isosceles triangle and this is also an isosceles triangle. And then how do we know that? Well, notice that if we plug in 60, we're going to get 45. And then here, this part here, if we plug in 45, we're going to get 60. So obviously these are isosceles triangles and they have the same area. 1/2 base times height, which would be 1/2 45 squared for both of them. So if we add them up, which is basically creating a square with them, it would be a square with side 45. Therefore, this area here and this area in total is 45 squared. So now all we have to do is divide this by the total area, which is 60 squared, and we're going to get the solution, which is 7/16. So now we're going to continue with probability calculation for equally likely outcomes using counting principles. So we're going to take a look at example 11.7. And it says, in a group of 18 students, 8 are females. So that implies that 10 are males. Find the probability of choosing 5 students at random, A, with all girls, B, with 3 girls and 2 boys, and C, with at least 1 boy. Okay, so for this type of problem in probability, we have to take into account a very basic principle. And that is that in an experiment where all outcomes are equally likely, the theoretical probability of A is equal to the number of outcomes that make up the event A divided by the total number of outcomes in the sample space. So the first question for A is, what is the sample space? Now the sample space is simply picking 5 students at random out of the 18. So that is a combination, right? So 18 in combination with 5. This is going to be the total number of outcomes of the sample space. And this is equal to 8,568. Now, we also need the number of possible outcomes for event A, and that is all girls. So that means in how many different ways can we pick from 8 girls, 5 girls? And this is equal to 56. So that means that the probability of event A is equal to 56 divided by 8,568. And this is equal to 0.0065. So for part B, they want us to see what is the probability of picking 5 students at random with 3 girls and 2 boys. Whenever you see the word and, this implies a multiplication. What do I mean by that? Well, the total number of outcomes for event B would be how many different ways are there of picking 3 girls from the 8, right? So 3 in combination with 8. And this times, because we have and as I said, how many different ways can we pick 2 boys out of the group of 10? So that would be 10 in combination with 2. So this is going to equal 56, which we had before, times 45, which is a total of 2,520. So the probability of B, remember, is going to be the total amount of possible outcomes for event B divided by the total number of outcomes for the sample space. So this is 2,520 divided by the total sample space, which before we found and was 8,568. So this is going to equal a probability of 0.294. For part C, we have to answer the question, what is the probability of choosing 5 students at random out of the 18 with at least 1 boy? So there's 2 ways of doing this. There's the long way and there's the short way. So let's do the long way first. So the probability of C is going to equal these combinations. Now notice we could pick 1 boy at least, so that would be 1 boy out of 10, and then this we would have to multiply times picking 4 girls out of 8. So that would give us a total of 5 kids. Now, this is mutually exclusive from other possibilities. So that means that or, which means plus, or we could do 2 boys out of 10 in combination with 3 girls. Or we could do 3 boys out of 10 in combination with 2 girls out of 8. Or we could do 4 boys out of 10 in combination with 1 girl out of 8. And finally, we could do just all boys, right? Which would be 5 out of 10. So all of this we would have to divide by the total possible outcomes, which we said was 8,568. So if you do all the math here, you would get 0.9935. So what is the short way? Well, look at it this way. If you talk about at least 1 boy, what is the complement? What is the complement of C? Well, the complement of C is having no boys, but no boys means all girls. So that means that the complement of the probability of C is the probability of A. So that means that the probability of C is equal to 1 minus the probability of A. And notice that this would give us the same answer because it's going to be 1 minus the probability of A, which we said before is 0.0065. So this would also equal 0.9935. So next we're going to focus on example 11.8. And it says, a deck of playing cards has 52 cards. In a game, the player is given 5 cards. So notice that that right there is the sample space for this problem, right? Which would be all the possible outcomes of picking 5 cards from a group of 52. So that's 52 in combination with 5. It says for part A, find the probability of getting 3 cards of one denomination and 2 cards of another, like 3 sevens and 2 jacks, for example. So let's take a look at a deck of cards. You have 4 different suits. You have diamonds, spades, hearts, and clovers. And how many denominations are there? Notice that if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So there are 13 denominations. Now, since the player first has to pick 3 cards of the same denomination, that means that he's going to have 13 different options, and this multiplied by 4 combination 3, because he or she has to pick 3 cards out of the 4. But we also have to take into account as well that after these first 3 cards are selected, there is going to be 12 denominations left, and he's going to have to pick 2 cards out of 4. So that means that the probability of event A is going to equal all of this divided by the sample space, which is picking 5 cards out of the 52. So if we do the math here, this is going to give us a very slight chance of 0.000144. So now we're going to continue with the other part of the problem. And it says, this game can be played in 2 stages. First, the player is given 5 cards, and then the player can decide to exchange some of the cards. And they put a note here. It says the cards exchanged are discarded and not returned to the deck. This is very important, not returned to the deck. A player was given the following hand: Queen of Spades, Queen of Diamonds, Queen of Hearts, 4 of Clovers, and 9 of Spades. She decided to change the last 2 cards. So that means that she discards the 4 of Clovers and the 9 of Spades, and she's left with 3 cards. And it says, find the probability for part B, find the probability of 1, 3 cards of one denomination, so 3 cards of one denomination, and 2 cards of another. So this is similar to the previous problem, but we have to take some things into consideration. For example, the sample space for this is now different because they have already taken out 5 cards. Remember that she discarded the 4 and the 9, but those are not put back into the batch. So that means that there's 47 cards left. Therefore, the sample space in this case is going to be, in how many different ways can you choose 2 cards out of 47? Okay, so now let's think about the numerator. It's 3 cards of one denomination and 2 cards of another, right? Now, 3 cards of one denomination we already have because she has 3 queens. So we don't have to worry about that first part. But then it says 2 cards of another. Since she's already discarded the 4 and the 9, that means that there's only 3 cards left with that same denomination. So that means that for the 4, there's going to be 3 cards left from which we have to pick 2. And then for the 9, it's the same situation. There's going to be 3 cards left from which we have to pick 2. Besides that, how many denominations are going to be left now? Well, notice that after these 3, the queens, the 4s, and the 9s, there's only going to be 10 denominations left. So there's going to be 10 ways to pick 2 cards out of 4 for each denomination. So that means that in this case, for part 1, I'll write it over here, the probability of this event is going to equal, first picking 2 cards that are 4s, so that would be the first combination, or picking 2 9s, which was the second combination, or the last one, which is 10 different denominations left, from which we have to pick 2 cards out of 4 possible ones. So then we divide all of this by the total sample space, which is picking 2 cards out of 47. Then we do this division, and we're going to get a probability of 0.0611. For part 2, they say, what is the probability of having 4 queens. The probability of this other event is going to be, now since there's only 1 queen, so we only have one way of picking 1 queen, and then if we pick 1 queen, there's going to be 46 different cards left, right? Because there's a total of 47. So it's going to be 1 times 46 divided again by the total sample space, which in this case we said is picking 2 cards out of 47. And this is going to be a probability of 0.0426.